Alright, so welcome to the next of our series of screencast videos for Math 1410 Linear Algebra. We're moving on now to look at lines in 3 dimensions. So we're on the home stretch for Chapter 3, the vector geometry. We've got a couple of videos on lines and then a few on planes, and then we will be finished with the Chapter 3 material. So let's jump right in. Now, just as a review how things work in 2 dimensions, I know everyone is pretty familiar with how lines work in 2 dimensions, right? So we have, you know, some sort of a picture like this, right? And we might think of a line as a graph, of a function like this, a function of one variable, and we might, draw something like, so b is the intercept value. So this thing, when x is equal to 0, y is equal to b, so you'd have a point 0, b on the line. And once you have one point on a line, if you know the slope, your rise over run, you can construct the line, right? And what makes lines sort of unique compared to other sorts of graphs that you might consider is that if you choose any 2 points on the line, this ratio, this rise over run ratio, right, change in x over change in y, this is always constant, right? It doesn't matter which 2 points you choose on the line, this ratio of the change in the y values over the change in the x values, this is always the same, right? So here, by delta y, I just mean y2 minus y1, and then x2 minus x1. Okay, so you have this constant ratio. So point in a slope tells you how to construct the line, and you probably remember doing some of these problems where somebody gives you a point. Maybe they don't give you the intercept, so they give you some other point on the line, some point x naught, y naught, and then you work out the slope, and then you have this this formula. This is often called the point slope formula for a line. Now, one thing you don't get with these types of equations, you don't actually get vertical lines if you write things this way. A vertical line doesn't really have a well-defined slope. I guess you could say it has infinite slope. The most general equation you can write down for a line in R2, sort of a general line, would look something like ax plus by is equal to c. And in the case where b is equal to 0, that covers your vertical lines. Otherwise, if b is not equal to 0, you can solve for y and get one of the other forms that we've written down. In 2 dimensions, the main feature of a line is that you've got two variables and they're related by this constant ratio, that when you change one, you know how much the other one changes, and this relationship between the two variables tells you pretty much everything you need to know about the line once you've got one point on the line. Now, once you move to 3 dimensions, things kind of come apart as far as this sort of approach, because you no longer have two variables. Now you have 3 variables, right? So you're dealing with 3 dimensions. So you've got a 3-dimensional coordinate system like this. So x, y, z. And of course one approach you could take is you could try to kind of, introduce multiple slopes. You could try to sort of, say how z changes with respect to x, and then say how it changes with respect to y, or something like this. Try to, give some not one slope but two, right? Because we can't really talk about slope anymore. Slope is something that takes place in a plane. And so you could try to give a pair of ratios, and there's some things you could do with that. You might be tempted to sort of, add one variable to this sort of, equation like we had here. This guy, you might just think about, maybe I'll just add a variable to that. But if you do that, well, you won't get the equation of a line, as we'll see later on. What you get is you get the equation of a plane if you try to do things that way. So just adding one variable to that type of equation doesn't work. You get a linear object, but you get something that's one dimension up. So how do you specify a line in 3 dimensions? Well, okay, so let's say I have 2 points, right? So I draw 2 points in space, and P, let's say Q is over here. So I'm not going to try to, indicate accurately where those are in space, but we've got a couple of points. Well, if I've got a couple of points, as soon as I have any 2 points, I can draw the line that passes through them. And of course, this is true in 2 dimensions as well, right? If I have any 2 points, if I have a point x1, y1, and if I have a point x2, y2, right, if I have these points, I can use those 2 points to reconstruct the slope, and once I have the slope, I can use either one of those 2 points to get the equation of the line. Right. So this idea that 2 points determines a line, this is something that remains valid if you go up a dimension. But how am I going to write down the equation of that line? Well, what you do now is you say, in 3 dimensions, how do you specify which way a line is going in 3 dimensions? Well, you want to now give a direction. You want to know which way that line is pointing. And we know how to give directions. If you want to give a direction, you give a vector. And we also know that if you have any 2 points, determine a vector, right? I can construct the vector PQ between those 2 points. And then if I wanted to get to some other point on the line, right, if I wanted to, let's see, mark some other point, maybe I'll mark it in black. Okay. So if I wanted to mark, say, this point R on the line a little bit further down, right, then I could try to draw this vector. Let me just kind of offset things a bit. Right, so I could draw this vector here, right? I could draw the vector PR. I drew it sitting a little bit off the line just so I don't mess up the picture, but we want to draw that vector kind of on the line as well. So what can I say about PR? Well, I note that this guy here it's parallel to the vector PQ, right? And what do we know about parallel vectors? We know that parallel vectors are scalar multiples of each other. And so what I can do is I can say that, well, this vector PR it's got to be some multiple of PQ. So there's got to be some real number t so that PR is equal to t times PQ, right? So t here is a real number. And so then what you can also kind of think, if you think about here, if you think about this t now as a variable, so you kind of think of this as some sort of like scalar variable here. Right? You can vary the value for t. If you make t bigger and bigger, you're going to keep going further and further out along the line, right? At t equals 1, you're kind of you're here at t equals 1, and then you go out here, you're at t equals 2, and so on. And of course, you can take values between 1 and 2. I could take, say, t equals 1/2 and start shrinking things, or I could also, of course, go into the negative numbers. I could get to, say, t equals -1, and I could end up, going down the other direction on the line. So this allows me to describe every point on the line. But we have to make one more modification because, of course, when we want to specify points in space, if we want to describe points in terms of vectors, we want to give position vectors. We want things that are anchored at the origin, and right now these vectors are floating out there in space. They're all anchored at this point P. So how do we fix that? Well, we know how to fix that. We just use the tip-to-tail rule for vector addition, and so what I can do is I can draw 2 more vectors. So I'm going to draw this guy here. Actually, let's make everything in blue. So I'll draw this vector like so. This will be let me just call it P with a arrow hat, the position vector for the point P. And I could draw this guy going to the point R, right? And so then what can I say in terms of the tip-to-tail rule here? Well, I can see that this vector R, what can I say about R? Well, R is equal to P plus T times PQ, right? Because T times PQ is this vector that we drew in black. Adding P to this vector PR gets me to the vector R, right? So this is kind of all we're really saying here is that the vector from the origin to R is, well, that's like going from the origin to P and then going from P to R, right? That's all that we're doing here, but we have a particular way of describing this vector PR. So if we write, if we let V equal to PQ, the direction vector, and often one of the notations you'll see is you'll see this R naught, R sub 0, to be P, right? So sort of the position at time 0, so you think of this here as like T equals 0. And often you could think of this scalar T as time if you think about kind of a particle moving along a line. Sometimes you think of this T as time. You don't have to think of it as time. So then you get something that looks like this. So you can think of R now, and if you want to, you can even think of it as a function of T is equal to R naught plus T times V. All right. So this gets you the vector equation for a line in 3 dimensions. All right. Now let's actually take that vector equation. Let's break it down. What do these things look like? So this, so we started with this guy here. So R of T is equal to R naught plus T times V. Okay, for our line going in space like this, right? Where R naught refers to some initial point on the line. So let's give that point coordinates: x naught, y naught, z naught. Okay, there's our vector R naught. We've got our vector V, which is parallel to the line, and let's say V has components A, B, C. And so if I have some other point on the line, so here's a point X, Y, Z, and we let R denote the position vector for any other point x, y, z on the line, then what we have is we have that x, y, z is equal to x naught, y naught, z naught plus t times a, b, c. And so then if I kind of equate components here, if I look at the x components and kind of break things down term by term, I get that x must be equal to x naught plus a times t. Y is equal to y naught plus b times t. Z is equal to z naught plus c times t. And so sort of an interesting thing happens because each one of these 3 equations, these are all linear equations. We can kind of, think of these are sort of in this format, y equals mx plus b, right? So this is kind of, I guess this is like your b. This is like the a, b, or the c plays the role of the m, and t plays the role of x, right? So it's this same sort of form that you're used to for writing in the equation of a line in the plane. What's interesting is you go up by one dimension, so you add a 3rd variable, and it turns out that the right way to do things is to actually add even one more variable. Suddenly this t comes out, and x, y, z, treat all 3 of them kind of equally. So we don't really, solve for one of the variables in terms of the other here the way we would in the plane. We treat x, y, z all as independent variables that happen to each of them depend on this one dependent variable t. This t, by the way, just in terms of some terminology, t. So t is sort of our dependent variable. Dependent variable. T is frequently referred to as a parameter, and then you would refer to these guys here as the parametric equations for your line. Okay, so we can do the vector equation or we can do the parametric equation. Either one conveys the same information, and you can use them interchangeably. It really doesn't matter which one you choose to use. There's another set of equations that you'll often see in textbooks, which are the symmetric equations. We're not going to worry about the symmetric equations in this course. It's not something that will be useful for us. All right. So that's kind of the introduction of the basic terminology and the setup here. Let's do one example before we go. So here we've got a couple of points in 3 dimensions. We want to come up with the line that passes through those points. So the first thing we need is we need a direction vector. Okay. So what is our direction vector? Our direction vector is this vector from P to Q. And remember, when we calculate the vector from P to Q, we do tip minus tail. So we do 2 minus 0, minus 1 minus 1, 4 minus 3. That gives me the vector 2, minus 2, and 1. If you want to, you can think of, one thing you might want to kind of keep in mind when you're doing some of these. Note that so the vector from P to Q is the vector from the origin to Q plus minus the vector from the origin to P. This is the head minus tail rule. If you rearrange this a little bit, this is saying that the vector from the origin to Q plus the vector from P to Q is the same thing as the vector from the origin if I do the vector from the origin to P plus the vector from P to Q, that's equal to the vector from the origin to Q, right? And so the way you kind of think of this is telling you, well, if you start at the origin and you travel from the origin to the point P, and then you travel from the point P to the point Q, right, you end up at the point Q. So it's the same as if you just travel directly from the origin to Q. So you can keep track of things these ways, and sometimes it comes in handy to be able to break things down like that. All right, so we've got our direction vector. We need any point on the line. We might as well choose, we can choose either one of the two that we're given. Let's choose our point to be given by the point P. So we'll take 0, 1, 3, and that gives me the vector equation. So x, y, z will be given by 0, 1, 3 plus t times the direction vector, 2, minus 2, and 1. And the other way you could do this is say, well, x is equal to 0 plus 2t, y is equal to 1 minus 2t, z is equal to 3 plus t. Okay, so we'll do some more examples with lines in the next video.